All right. Hi there, Chemistry 3101. Today we're going to be talking about chapter 14, which is a real departure from chapters 1, 2, 3, and 4. So you can see we're skipping quite a bit of content here to get up to chapter 14, which deals with infrared spectroscopy and mass spectrometry. But be reminded that after this chapter, we're going to go right back to chapter 5. Okay, so let's talk about what infrared spectroscopy and mass spectrometry are to begin with. Well, first of all, you see that there's spectroscopy and spectrometry. So spectroscopy is the interaction between matter, and light. Okay, so matter and light, that's what spectroscopy is. So in chapter 15, we talk about nuclear magnetic resonance spectroscopy. So again, that's the interaction between matter and light. And we know that there are many forms of light, right? You know about the electromagnetic spectrum. So you know about UV light and infrared light, invisible light, and radio waves and all that stuff. And then when we talk about mass spectrometry, so spectrometry deals with the interaction between energy and matter, or matter and energy. So one deals with energy and the other one deals with light and their interactions with matter. Now, where we're going to start today is talking about infrared spectroscopy. Infrared is where we're going to start, and that actually covers probably 70% of the content in this chapter. And if you're wondering, what's the purpose behind infrared spectroscopy, this whole interaction between matter and light? Well, the purpose of infrared spectroscopy is to identify functional groups. Functional groups. And if you think about what is the goal of science, right? It's to, or what's our goal as a scientist is to push the boundaries of science, right? It's not to do things that have been done over and over and over. We don't want to repeat that. We want to discover new molecules. And let's say you make a new molecule. Well, how do you determine the structure of that molecule? Well, you need several forms of spectroscopy and spectrometry, but with infrared spectroscopy, you can determine the functional groups of the compound. And so what that means is you run an infrared spectrum on your organic molecule and you can say, well, hey, maybe this molecule is a ketone, or maybe it's an alcohol, or maybe it's an amine, right? This is the kind of information, and we could put here, etc. This is the kind of information that we're going to get from an infrared spectrum. Later on in mass spectrometry, I'll get into more of the detail of why we do mass spectra, but the purpose behind mass spectrometry is to usually determine the molecular formula. So I'll just put this here. We'll say molecular formula. Molecular formula. And if you're wondering, well, what can you get from a molecular formula? It's not a whole lot of information. Well, there's actually quite a bit of information packed inside a molecular formula, but we'll get to that later. So before we can get into spectroscopy, which I told you is the interaction between what? It was the interaction between matter and light. You have to understand what light is. And we know that light has a particle property, and it also has a wave property as well. And if we look at the wave component of light, which is electromagnetic radiation. So remember, light, and electromagnetic radiation are synonymous. And when we talk about light as electromagnetic radiation, you can see that light is made up of two perpendicular oscillating fields. We have an electric field and a magnetic field. So a little more about light. It says here that light can be thought of waves. So we can think about light as a wave, or we can think about it as particles. So waves of energy, or packets or particles of energy that we call photons. And it says here that the energy of each photon is directly proportional to its frequency. So we have here energy is equal to h times nu. So you need to know that h is Planck's constant. So Planck's constant. And you don't have to memorize Planck's constant for this course, but it's 6.626 times 10 to the negative 34 joules times seconds to the minus 1, like that. And then frequency, so let me double check something here quickly. Yeah, I knew I had the units wrong. I was like, that doesn't cancel, does it? It's joules times seconds, right? Because frequency is measured in seconds to the minus 1. So if you multiply the two, right, joules times seconds multiplied by seconds to the minus 1, the seconds cancel and you end up with joules. That's a little bit better. And then it says here the wavelength is inversely proportional to energy. So we've covered that Energy is directly proportional to frequency. You see that here, energy and frequency are directly proportional. But you should remember from your general chemistry days that the speed of light, which is c, is equal to wavelength times frequency, like that. And so if we rearrange this and solve for frequency, we get that frequency is equal to the speed of light over wavelength. Now, if we plug the frequency is equal to c over lambda into this formula, what we get is E is equal to hc over lambda, like this. And so now we see the energy is inversely proportional to wavelength. So again, what's our take-home message? A couple of things. Energy is directly proportional to frequency, and energy is inversely proportional to wavelength. So what does that mean? It means the shorter the wavelength, the higher the energy. The longer the wavelength, the lower the energy. And of course, you probably remember the speed of light, which is approximately 3.00 times 10 to the power of 8 meters per second. Don't stress, you won't be doing any calculations in this class, just kind of putting some numbers to it here. So going back to the electromagnetic spectrum, this is something that you would have covered in detail in General Chemistry 1. So if you took it at UCCS, you should have covered this in detail in Chemistry 1401. So you would have memorized the electromagnetic spectrum. And if you haven't, you should have. Okay, so it says here we go from microwaves and radio waves, which are really long, and then we go up to infrared. And of course, this is what we're going to be interested in chapter 14. Then we get it up to into near infrared, visible, ultraviolet. Then we get up to vacuum ultraviolet. Anyhow, you don't need to separate the two types of UV. Then we get into X-rays and gamma rays. And what do you notice is that if we look at high energy, and high energy and low energy light, okay, or electromagnetic radiation. Remember, light and electromagnetic radiation, they mean the same thing. You can see that if we have a short wavelength, so we have short wavelength and we have high frequency, it's going to be the higher energy waves of light. And then down at low energy, this is where we have low frequency and we have long wavelength, like that. All right. So with that in mind, it says here that when light interacts with molecules, the effect is going to depend on the type of light that's used, so the wavelength that is used. Now, I've covered this with you already this morning, is that infrared spectroscopy is used to determine the functional groups present in a compound. And then in chapter 15, so later on in chapter 15, we're going to cover the topic of NMR, nuclear magnetic resonance spectroscopy. And for NMR, we use radio waves. And the idea behind NMR is that we can actually determine the arrangement of carbon and hydrogen atoms in a compound. So we actually get information about what we call the connectivity of a compound, or the way that the atoms are connected together. But again, we're going to look at that another day. And a topic that isn't covered in this class, so again, this is chapter 14. A topic that we don't cover is ultraviolet visible spectroscopy, which gives you information about conjugated pi systems. Again, we don't cover this, okay? So not, we could put here, not covered in this class. So you don't have to worry about UV vis spectroscopy in this class. So again, what are we going to be focusing on this morning is an infrared spectroscopy. We're going to be talking about how we can determine what the functional groups are that are present in a compound. But before we get into that, we have to talk a little bit more about molecules and how they behave. So it says here that matter exhibits particle-like properties. And if we think about a particle on the macroscopic scale, because we know there's a difference between particles on the microscopic scale, which exhibit quantum behavior, and particles on the macroscopic scale, which do not exhibit quantum behavior, but rather exhibit continuous behavior. Think about this wheel, okay, spinning here, okay? If we think about that wheel, okay, that is macroscopic, okay, we can see that, and we know that things that are on the macroscopic scale exhibit continuous behavior. So if you don't know what that means, let me explain it to you. What it means is this: when it says continuous behavior, it means if I asked you to spin this tire, I said, I want you to spin this tire around, Jennifer, at 10 miles per hour. You could do that. If I said spin this tire at 10.1 miles per hour, right? 10.1 miles per hour, mph. You could do it. If I said 10.12 miles per hour, you could do it. 10.129 miles per hour. You could do it, so on and so forth. And there's no limitation to the precision or the rotation that we could get, right? We could get any speed that we want. We're only limited by the sensitivity of the equipment that we're using. Well, the thing is that molecules do not behave that way, and it's difficult. Sometimes it can be difficult for us to understand, is what I should say. But quantum behavior is more like this. Okay, quantum behavior would be this. It would be, I would ask you to spin the tire at 10 miles per hour, and then I say speed it up. And when you speed it up, it goes immediately to 11 miles per hour. There's no speed in between. It doesn't exist. Okay. Then I say, make it go faster. And then it goes up to 12 miles per hour. Keep in mind, this is just an example. But the idea with quantum behavior is that there's nothing in between, and you're like, well, that's impossible. How can you go from 10 to 11 directly? It has to pass somewhere in between as it gets faster. Well, not on the quantum scale. Okay. Now, there are examples of quantum behavior in our everyday lives. If you think about when a hen lays eggs, okay, the hen lays what, 3 eggs or 4 eggs. You don't say, oh, I went to the hen house and this hen laid 3.2 eggs. It exhibits quantum behavior. And if you're a musician and you know anything about the musical scale, that exhibits quantum behavior as well, right? There's no notes in between. Of course, you can bend notes, and I understand that, but within the scale, there's only certain frequencies that exist. Anyhow, so that's the idea of quantum behavior. And molecules, and what we're going to see is that bond vibrations exhibit quantum behavior. Okay, give me a thumbs up if you're even part of the way with me on quantum behavior versus continuous behavior. It's not an easy thing for us to understand, but it is something. Another example that I give of quantum behavior is, just counting people. When we count students in the classroom, I can say there's 14 of us online together right now. I would never say, oh, look, there's 14.2 students today. So that would be quantum behavior as well. But on the molecular scale, matter exhibits quantum behavior. And so what that means is that a molecule will only rotate or vibrate at certain rates or energies. Now, let me unpack these words here: rotate or vibrate. If you have a sample of some kind of organic compound, right? Let's say you have some kind of bottle, and then you've got some molecules in here, right? Let's say doesn't matter what it is. Let's imagine it's cyclohexane or something. You've got a bottle of cyclohexane, which happens to be a liquid at room temperature. Well, you guys, if you've never been told, I'm sure you figured it out by now that the molecules are moving around, right? They're tumbling around inside the bottle, right? Matter only ceases to move at 0 Kelvin, which is absolute zero, and that's a theoretical temperature anyway, right? So the molecules are moving, and then also inside of the molecule, the actual bonds are actually kind of flexing back and forth. So they're getting longer and shorter. They're stretching a little bit. Okay, there's a little bit of wiggle room in there. And the word that we use for that is a vibration. Okay, I get it that it's a little bit different than the word than how we use vibration in our everyday life, right? If you are talking and then you touch the side of your neck or something, you can feel a vibration. Or when a car is running and you put your hands on the hood, well, then you can feel a vibration. I understand that we're using it in a little bit of a different way, but when it talks about the bonds getting longer and shorter, kind of flexing like a spring, okay? So it's like they're exhibiting, we'll put here, spring-like behavior. That's what vibrations mean in organic chemistry. And again, I get it. It's a little bit different than our everyday life, but that's what it means. It means the bonds are kind of vibrating or stretching and shortening like a spring. Okay. And I'm going to show you some more examples of that as we move along here. But the idea is this: if you have two atoms, okay, I'll make the simplest possible atom that I can, just a blue sphere. Okay. If I have two blue spheres, okay, attached together by a bond. Imagine these are just two carbon atoms. Okay, we can think about the bond as being like that. Okay, a bond, and then you say, oh, there's two electrons in that bond. I get it. There's nothing wrong with thinking about it that way because that's what we usually think. Okay, but the way we think about it in infrared spectroscopy is more like this. It's more like the atoms are attached by a spring. Okay, this is the bond. Okay, and then the bond can get longer and it can get shorter, right? Just like a spring can stretch and compress. So we call those vibrational um, vibrational energy levels. Okay, and so we can have a low energy vibrational state where the spring is stretching back and forth slowly, and then we can have a high energy vibrational state where it's stretching back and forth very quickly. Okay, and if you're thinking, is this like a spring bouncing up and down? Yeah, essentially that's what we're thinking about. But again, the idea is that molecules are so small, they exhibit quantum behavior. And so that stretching can only happen at this level. And then it can happen at this level with this frequency and this frequency and this frequency. Now, a couple of things I want to unpack here before I move to the next slide is, again, if you're angry at me and saying, well, no, it's got to be somewhere in between as well for it to go to the next energy level. I get it, that it's difficult for us to think that way, but that's the way that matter behaves at the very small level. Okay, so at the macroscopic level. So that's the first thing. And the second thing is, you just heard the word frequency come out of my mouth, and I said as the frequency increases. Well, again, you remember this formula that energy is equal to Planck's constant times frequency. So again, energy is directly proportional to frequency. So as the energy goes up, so does the frequency, right? So high frequency, so that means it's going to be stretching back and forth very quickly, because remember that frequency is cycles per second, right? So if it's stretching back and forth very quickly, that's high energy, it says here high energy vibrational state, but you would also say high frequency. And then of course you would have low energy, low frequency. Again, I don't mean to keep bugging you guys, but give me a thumbs up if you're part of the way with me on this, even like 50% of the way, and you're sitting pretty, okay? Because you're going to have to read it, all right? It's something that we all have to do, figure out quantum behavior. So again, unpacking this whole idea of quantization. It says here that for the electrons in covalent bonds, where's my highlighter? Vibrational energy levels are separated by gaps, right? They're quantized. And again, that was what we saw in the previous slide, where you had energy increasing like this. And then we said you had this energy level, this energy level, this energy, so on and so forth. But there's nothing in between. So if a photon of light, so if it gets hit with a photon of light, so say you have something at this energy level, and then you shine, right? Energy is equal to h nu. So you shine energy at this, with just the right frequency, it's going to be able to go from this energy level to this energy level like that. And when it does that, when it jumps up, we call that vibrational excitation. Okay, so the infrared light generally causes molecular vibration. Remember, vibration is just the bond stretching back and forth. And it says here, here's where the money is. Here's where it gets really fascinating. Okay, I'm going to highlight this in green. Different types of bonds absorb different IR energies. Oh, here's where it gets really good, because now we can plot the frequency of light versus the type of vibration that we're getting. So I guess, how would I phrase it? You could plot the frequency. We're going to get different frequencies for different types of bonds. So if we look at the different absorptions at different frequencies, they'll tell us what kind of bonds we have in the molecule. Now, it says here that eventually the absorbed energy is released from the molecule as heat. So infrared energy is released as heat from the molecule. And that's what we're looking at in our infrared spectrum, is the heat or the energy that is released. Now, going back to the vibration idea, okay, and I've gone over this quite a bit already today, but it says here that molecular bonds can vibrate by stretching or by bending. Now, what we're going to concentrate on in Chemistry 1401 is going to be stretching vibrations, okay? This is what we're going to concentrate on in Chemistry 3101 is what we're going to concentrate on, stretching vibrations. You do have to be aware of these other kind of vibrations as well. And I would say that those are covered in greater detail in the lab in Chemistry 3102, but they are pertinent for us as well. Now, the whole spring stretching like this, students usually understand that, it's just a spring bouncing back and forth. Okay, and again, that's what we're going to concentrate on in this class. But when you look at these other type of 3 atom, right, 1, 2, 3 atom, we have something called scissoring here, and then we have another one called twisting. Well, they always say I shouldn't look at Wikipedia. Well, I'm going to break that rule this morning and show you something kind of quickly here. is that if you look at Wikipedia, oh, I thought I had it pulled up. I'll find it later, where it shows you. Just give me a second here. Just bear with me for 2 seconds. I'm going to see if I can dig it up here, and I'll start presenting again. So, there we go, found it. Okay, so if you go into Google and you type in Wikipedia infrared spectroscopy, and again, I'll start presenting in just a second here. So what you're going to see is something that looks like this. So where is it? Right here. Okay, so these are the different types of 3-atom vibrations. Now you see we have symmetric stretching, we have asymmetric stretching, then we have scissoring and rocking, and I think those are the ones that were in the slides. But these are the different types of 3-atom stretching or vibrations that we can have. So all of these are called vibrations, okay? And really the only one that's going to come up in today's lecture is actually the first one, where it says symmetric stretching and asymmetric stretching. If you want to make a note, if you're making notes while I'm lecturing, that is actually seen in primary amines. Okay, so in a primary amine, we see symmetric and asymmetric stretching, but the rest of them, like the scissoring, rocking, wagging, and twisting, I'm not going to ask you anything about those. Okay, so don't worry about them. But they are really cool animations that show you what the stretchings are referring to. So again, what we're mostly concerned with in this class are going to be the stretching vibrations like a string, bouncing back and forth. All right, so I'm not going to lecture on the night vision goggles or the cancer detection using infrared spectroscopy. You can take a look at that if you want. It's yeah, I'll just leave that as an FYI. I won't test you on that. Okay, so here's where this is going to be something that's more pertinent to us. Now, like guys, different types of bonds are going to absorb different frequencies of light, and we see that shown here on this slide. What are the 2 of the most common types of bonds we see in organic chemistry? Well, we see lots and lots of carbon-hydrogen bonds. There's no doubt about that. And we see plenty of carbon-oxygen bonds. We see these in alcohols, and we see them in esters and ethers. So you notice that there's a different energy gap between the stretching frequencies or the vibrational energies between the carbon-hydrogen bonds and carbon-oxygen bonds. So we see we have a larger energy gap. So that means a higher frequency, right? Because energy is equal to H times mu, like that. So higher frequency for a carbon-hydrogen bond, higher frequency of light, higher energy, bigger energy gap, however you want to say it. And then for a carbon-oxygen bond, we have a smaller gap or a lower frequency, however you want to slice it. But again, if you're sitting there at home and going, what's the relevance of all this? The relevance is this, is that since energy is directly proportional to frequency, right? These absorb at different frequencies. One has a large frequency, the other one has a small frequency. We can actually plot that, and we're going to take a look at what that, if you're like, well, what does the plot look like? And we're going to take a look at that in just a few minutes. You'll just have to bear with me a little bit longer before we start getting into looking at some actual spectra. So if you're wondering, what does an infrared spectrometer look like? Like, what kind of instrument do you do this? Run these infrared spectra on? Well, this is what a spectrometer looks like in 2024. It's really, wonderful instruments that we have now. We actually have 2 of these at UCCS. So we'll do it in chemistry, right? We'll put a stoichiometric coefficient of 2 times UCCS. So we have 2 of these, and these are really great infrared spectrometers. So what it says is you put your sample in the spectrometer. So you actually put your sample here, and then it irradiates the sample with all relevant frequencies of infrared light. So if you go back a few slides, you'll see, so if we go back, I don't feel like doing it, but anyhow, we'll go back here. So we see the IR says, from 70, so from 700 nanometers all the way down here to 50 micrometers, whatever, that's neither here nor there, but the whole range of frequencies. So we hit the sample with all the pertinent frequencies in infrared light, and then the frequencies get absorbed by the sample. And then from the absorbances, we can tell what type of functional groups are present in the compound. Now, the old spectrometers used to use sodium chloride plates. These are still used, the sodium chloride plates, But now the sample is usually put right in the spectrometer. Okay, it's put right on there. There's like a lens that you put it on, and they work really, really well. So here is an infrared spectrum. Okay, this is your initiation into infrared spectrum. But a couple of things that we'll go over here is that you see you have percent transmittance on the y-axis. Then you have this new unit down here called wave number on the x-axis. So it says an infrared absorption spectrum plots percent transmittance as a function of frequency. Now you see here that this thing here, which is wave number, so wave number, put it here. The symbol that we use for wave number is in nu, the same one as frequency, but you put a little line above it. Okay, so it's just the nu, but you put a little line on top, and that represents wave number. So when you boil it down, what our textbook says is it says that wave number is equal to frequency divided by the speed of light. Another way you could phrase it or frame it is that wave number is just inversely proportional to wavelength. But what you get from this formula, and again, this is the one that's shown in your textbook, okay, is that wave number and frequency are directly proportional. I'm not going to ask you to derive a wave number or anything like that. All you really need to know is that if you're at a high wave number, so you see that wave number ranges from 4,000 to 400 centimeters to the -1. So if you're at a high wave number, you would say that this is high frequency. And of course, if it's high frequency, then it's going to be high energy. And then down at the bottom, if you're at a low wave number, you'd say it's low frequency, and you would also say it's low energy. Of course, you could also describe it in terms of wavelength as well, but we usually don't do that, okay? So let's go back to this spectrum and look at a couple of things. I bet you noticed that the wave number scale isn't linear, right? You see that the divisions here are 100, and then when you get here, you can see how they get smaller. Well, that is just a standard. That's just the way that we always plot the spectrum. Okay, so we have wave number down in our x-axis, and then the percent transmittance. This tells us how much of the infrared light is coming through. So if you look at the top of the spectrum, let's say you look around, greater than 90%, something like this. If you draw a line up here, what you'd say is everything everything that's kind of above here, you would say anything that doesn't absorb light here, you'd say that the light is transmitted all the way through, okay? And so there's no absorption. So what I mean is something like this, right? If there's no light absorbed up here, it means that everything was transmitted through, and so there was no absorption at that frequency or at that wave number. So what we're actually interested in is where the absorption bands are. So where are the absorption bands? Well, this would be an absorption band here. This would be one here. There's one here, 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 so on and so forth. Even this is a tiny absorption band, which may or may not be pertinent depending on what the molecule is. But where we have absorbance, so where you see where there's very little transmittance is low, so absorption is high. Absorption bands are what we're interested in as organic chemists. So again, here's that formula that is given to you in your textbook, okay? So again, you guys know that the speed of light is equal to wavelength times frequency, like that. So we could say that frequency is equal to c divided by a wavelength. So if you plug that in here, you get wave number is equal to c over c times wavelength. So you could also say that wave number, right, is equal to 1 over the wavelength. So either way, you can say that wave number, like I said, is directly proportional to frequency or is inversely proportional to wavelength. Doesn't matter, okay? And these are the range of values that we use, is 400 to 4,000 reciprocal centimeters, okay? There's basically every IR spectrum that you see is going to go from 4,000 to 400 reciprocal centimeters. The next thing, besides the wave number, that are going to be relevant to us will be the intensity and the shape of the peak. So what do I mean by intensity? Intensity means, how much of it is absorbed, okay? So you could say strength of absorption. So for intensity, we could say strength of absorption, okay? Like this. So you see that, the absorption here is really high, right? Because there's very little transmittance, right? You'd say this is a high absorption. So these are very intense peaks, right? a lot of absorption here. This is intense. This is intense. And then we have the shape. So the shape, you see that some of the peaks or some of the absorption bands are sharp and some of them are broad. So we'll just put here sharp, sharp versus broad. Okay, like this one here is quite broad, whereas this one here is quite sharp. Okay, and there's some relevance to that as well. And if you're wondering, could you give me more information on that? Well, we're going to unpack both of those a little bit more. Okay, so before we get into the intensity and the shape, what we're going to talk about is that wave number idea. Okay, so when does something have an absorption at a high wave number, and when does a bond have an absorption at a low wave number? So it's based off of two things. Okay, so remember this wave number or your stretching vibration. Okay, so again, I'm just rehashing the same ideas over and over, but the frequency or the wave number, right, of your stretching vibration, remember that wave number is equal to frequency over C, right? So this one is wave number, okay? And this one is frequency. They're both directly proportional to each other. So the frequency or the wave number for a stretching vibration depends on two things. Number one, it depends on the strength of a bond. Is that something we've talked about before? Of course, okay? A triple bond is stronger than a double bond. A double bond is stronger than a single bond, right? And the next thing is the mass difference of the atom. So where would you get the mass of an atom? From the periodic table? So bond strengths and the mass of an atom, these are things that you know about. Now, if you look at this giant formula here, you might be intimidated by this. If you look at this, wave number is equal to 1 over 2 times pi times the speed of light multiplied by, remember, to the power of a half is the same thing as the square root of, okay? So the square root of F, which turns out to be the force constant, divided by m, it says here mRED, which is the reduced mass. So if you've studied physics at all and you've talked about springs, then you know F is equal to ma, and you would have looked at F is equal to, if you ever looked at F is equal to kx, okay, and you talked about a force constant. Anyhow, that's physics, but the idea is this, is that if force constant, which is F, is bond strength, it means the stronger the bond, the bigger this number, okay? So stronger bond equals greater F. And then of course a weaker bond would be a lower F. So what does that tell you? Well, if wave number is directly proportional to the square root of this, force constant divided by the reduced mass, this tells you that the stronger the bond, the higher the absorption. So the greater the wave number. So you could also say here, greater wave number. So what does that tell you? Stronger bonds are going to be found to the left on your spectrum. And then reduced mass is just this formula down here, which is the product of the masses of the two elements in the two atoms in the bond divided by their sums. So what does that tell you? It tells you that the heavier the atom is going to have a lower wave number. So you could put here, and then the lighter the atoms is going to have the higher wave number. So let's just put here, we'll put here lighter. Actually, it's written at the bottom, isn't it? Okay, smaller atoms or lighter atoms are going to have a higher stretching frequency, and then of course, larger atoms are going to have lower stretching frequencies. So there you go. So again, you do not have to memorize this formula whatsoever. What I would memorize is this: is you should know that wave number. Okay, so I would write wave number like this. Wave number is directly proportional to the force constant, and wave number is inversely proportional to the reduced mass. Those are the two things that you need to know. All right, so let's see some examples of this. So here are just some different bonds. Let's start with number 2. I think that one's, I don't like to use the word easy in organic chemistry, but I think that these are faster for students to pick up on, right? Because everybody who's hearing the sound of my voice knows that a triple bond is stronger than a double bond, and that a double bond is stronger than a single bond, right? There's no mystery there. So if our wave number is directly proportional to our force constant, what does that tell you? Stronger bond, so the triple bond between carbon and nitrogen comes at a wave number of about 2200 centimeters to the -1, whereas the single bond is all the way down at 1100 centimeters to the -1. Give me a thumbs up if you're just with me on concept 2. Stronger bond, higher wave number. weaker bond, lower wave number. Cool, okay? And then the one on the top involves the reduced mass. You can see that they're all bonds to carbon. So let's say M1 remains constant. And I'm not going to do the math. If you need to grab a calculator and try the math on this, I mean, if you guys know how to multiply, divide, and add, okay? But you can see how as you change the size of the atom from a hydrogen to a deuterium to an oxygen to a chlorine, what's happening is that the atoms are getting bigger and bigger, and so they're getting heavier. And what did we say? That if the mass increases, that the reduced mass increases, and so then we absorb at a lower wave number. So whenever you have a bond to anything that's bound to hydrogen, I mean, hydrogen has a mass of 1. Okay, so anything that's bound to hydrogen always has a really high wave number. Okay, because you might be thinking, well, it's only a single bond. Why is the wave number so high? It's because hydrogen's mass is so low. It's a mass of 1. It's the lowest mass you can have. Then you get down to something like chlorine, which is really heavy, has a mass of 35, and then you see that the wave number is significantly lower on our scale from, what was it, 4,000 to 400 reciprocal centimeters. So what are some conclusions that we can draw? Okay, everybody who's listening to me is a scientist, right? We're all interested in drawing conclusions, right? And kind of connecting dots and looking for patterns. Well, based off of that formula, okay, we said that wave number was directly proportional to bond strength, and we said that wave number was inversely proportional. I'll just put 1 over the reduced mass like this. So what do we see? Okay, the weaker the bonds, the lower the wave number, right? So we see single bonds are way down here at the bottom, double bonds are going to be higher, and then triple bonds are even higher than them, right? Okay, well, that makes complete sense based off of this. The stronger the bond, the higher the wave number. Now, if you notice up here, we have a single bond, okay, and you're like, well, single bonds are the weakest. Why are these up so high? Well, again, I already covered this, okay? It's because hydrogen has such a low mass that its reduced mass is always going to be very small, okay, compared to whether you have double bonds and triple bonds, etc. And so anything that has a bond to a hydrogen, whether it's I'll just get a finer tip here, whether it's carbon to hydrogen or oxygen to hydrogen or nitrogen to hydrogen, etc., those are going to be found at a high wave number. Why? Because the reduced mass is so small. Okay? Any questions up to this point? And I know I'm repeating myself a lot. I totally get that, but I think that some of the concepts here are so different than what we covered when we're talking about nomenclature, you know, or acid base, chemistry, that it bears repeating. Okay, cool. Give me a thumbs up if you're with me on these ideas, on these two concepts. Everybody with me on these ones, even part of the way? Okay, cool, cool. If you understand this, my friends, if you're like, yep, I get this, stronger bond, it's going to have a higher wave number. And yeah, I totally get this, that if you have a hydrogen, it's going to be a high wave number because it's got a mass of 1. If you have a big old heavy atom like a bromine or something, it's going to have a super low wave number because it's so big. Its reduced mass is going to be so large. If you understand those concepts, man, you are off to the races on infrared spectroscopy, okay? All right, so if we take a look at this kind of plot of wave numbers and types of bonds, we can actually break this down into 2 main regions, okay? So what our author did is he drew a line here at 1,500 reciprocal centimeters. Anything below that, we call that the fingerprint region, and everything above 1,500, we call that the diagnostic region. I'll just level with you. In Chemistry 3101, we're going to spend most of our time in the diagnostic region because it provides much more clear information. I kind of call it the low-hanging fruit. You can kind of look at it very quickly and make an assessment. And you might think, well, then we'll never the fingerprint region won't be relevant for us. It's not true, because if you think about 2 people that look very similar, you might not be able to tell them apart, but you can tell them apart by their fingerprints, can't you? Absolutely, you can. And so it's a similar kind of thing with compounds. Okay, it's a very similar kind of thing with compounds, is that you might have 2 compounds that have diagnostic regions that look almost identical, and you're like, oh, I won't be able to tell these apart until you get into the fingerprint region, and then you can absolutely tell them apart. So it's kind of cool, the fingerprint region. So here's 2 examples, okay? The one on the left is 2-butanol, so you see structure right here, and the one on the right is 2-propanol. You see the compounds are pretty similar. They're both alcohols. Everybody in this who's hearing the sound of my voice could recognize an alcohol. But if you take a ruler and you draw a line at 1500 reciprocal centimeters or centimeters to the -1, whatever you want to call it. Sorry, Mr. Dion's trying to draw a straight line here. But anyhow, where's my pen? If you draw a line, come on, pen. There we go. If you draw a line here, take the ruler. And why does that look crooked? There we go. Maybe that's better. Okay, you draw a line here. What I'm trying to get at is if you look at the region to the left of these blue lines, so here and here, they're almost identical. Okay, you see you have this big, broad absorption here. Then you have this kind of sharper one here around 3000. They don't look that different. You even have some kind of, something up here and something up here. So they look pretty similar. But if you look in the fingerprint region, and I'm sure you've been looking while I've been talking, you notice they're hugely, like look at these 3 giant absorptions here. They're not even here, okay? So there's a huge difference in the fingerprint region between these two. But again, we're not going to spend much time in the fingerprint region, very little. We will spend some time there because there are some, excuse me, really good pieces of information in the fingerprint region. But like I said, we're going to spend most of our time in the diagnostic region. So let's stay on this theme of wave number, okay? So if you're kind of sitting there going like, where are we right now? So what we've covered is when wave number is high, it's going to be a strong bond or a bond to hydrogen. And when wave number is low, it's usually going to be a single bond to a heavy atom, okay? So if you take a look at the 3 bonds that are shown on this page, you guys remember sp3, sp2, and sp hybridization, of course. I mean, these came up in the chapter on acids and bases, didn't they? Well, you can actually tell the difference between these 3 different types of carbon-hydrogen bonds, whether your carbon is bound, your hydrogen is bound to an sp3 hybridized carbon, sp2, or sp. So check this out. You notice that the wave number, or the absorption for the carbon-hydrogen bond with the sp3 hybridized carbon is significantly lower than when we have an sp hybridized carbon, and then sp2 is somewhere in between. Well, a couple of things. Of course, I'm your teacher. I'm going to explain to you why they have different stretching frequencies. But before we get into that, this is like gold, Jerry. I mean, this is such good information because now this enables us to differentiate between all these different types of carbon-hydrogen bonds. I mean, that's very valuable information, right? What if you're trying to identify a terminal alkyne? Well, you'd want to try to look for an absorption at 3,300 centimeters to the -1. So it says the higher the S character, so the more S character the carbon has, then the stronger the carbon-hydrogen bond, and so the higher the stretching frequency. If you don't remember this whole idea here, higher S character, stronger the carbon-hydrogen bond, let me remind you, okay, I don't have it in the slides here, but when you go from an sp3 hybrid orbital to an sp2 and then down to an sp, they actually get smaller and smaller. So as they get, and this is not the best artistry in the world, but as they get smaller, the overlap between the carbon and the hydrogen becomes closer, and so the bonds get stronger. That's all you really have to know for this class. But if you take a look at these carbon-hydrogen bonds in these spectra, look, we can differentiate between an alkane, an alkene, and an alkyne. Check this out. This is just great stuff. So if you draw a line at around 3,000 reciprocal centimeters, so you see that the red line in all of these, they're all drawn at 3,000, okay? And if you're wondering, should I do that on a spectrum? It's not a bad idea, I can tell you that. So if you take a look at the alkane, what do we notice? What did it say on the previous slide? It said, below 2,900 or something. So you see all of this stretching here, okay, or all of whatever you want to call it, an absorption band or stretching. That means that this carbon is sp3 hybridized. So we oftentimes see absorptions just below 3,000 centimeters to the -1. Why? Because sp3 hybridized carbon-hydrogen bonding is so prevalent in organic molecules. But then if you have an alkene or maybe an aromatic, somewhere where you have a bond between an sp2 hybridized carbon and a hydrogen, well, then you would look for an absorption around 31. So if you take your ruler, okay, and you draw a line There's my ruler. Draw a line here. It's not perfect, but you can see that it's greater than 3,000. Okay, so it's close to 3,100. And then with the alkyne, okay, and again, if you're wondering where you're getting these numbers from, right, the alkyne, it says it's close to 3,300 reciprocal centimeters. Well, let's go over here. If you take your ruler and you draw a line here, I mean, the whole scale isn't shown on here, but you can see that this is pretty close to 3,300. And so that would be a giveaway that we have that sp hybridized carbon hydrogen stretching. So again, and I know I'm repeating myself a lot, but trust me, it bears repeating. Now what we see is in these spectra, we can differentiate between an alkane, an alkene, and an alkyne. Is that something that might be useful for an organic chemist? Oh, you bet your Bobby socks it is, okay? Being able to distinguish between alkenes and alkynes, which are functional groups, and then just an alkane, which does not, remember, an alkane is not a functional group, okay? All right, so now, I would be the first person to admit that doing a science degree is not easy, definitely not for the faint of heart, and that studying organic chemistry can be frustrating at times. I teach you a lot of rules, and then I go over a lot of exceptions to those rules. And here are a couple of exceptions that you need to know. Based off of what I just told you, you might think, oh boy, well, every time I have an alkene, I'm going to have a stretch at around 3,100. Every time I have an alkyne, I'm going to have that stretch around 3,300. Well, it turns out that it's not true. And why would that be? Okay, well, let's think about it. Is this an alkene? Absolutely, that's an alkene. Okay, hopefully you can see it. There we go. So this is an alkene on this slide. But is there a carbon-hydrogen bond? Here are your two sp2 hybridized carbons. These are all R groups. They're not hydrogens. So just because you don't see something doesn't mean it's not an alkene, right? Just because you don't see that signal at 3,100 doesn't mean it's not an alkene, okay? So you kind of have to be on your toes about that one. And the next one, look at this. We have two sp hybridized carbons, but this would show no signal at 3,300. Why? Because these are two R groups. They're not hydrogen atoms, right? So just because you don't see the signal at 3,300 doesn't necessarily mean you don't have an alkyne. Now, before you start to panic and say, oh my goodness, now all the questions he's going to ask are going to not give me the information. Remember, that's not my job, okay? I'm always going to give you enough information to solve the problem. I'll always provide you with enough information, but you need to be aware of this, okay? So I'll just write this on here. Be aware of these, okay? And if you're wondering, well, maybe they'll never come up. Oh, they come up. There's definitely situations where they come up. So it is something we need to know as organic chemists. All right. You guys remember chapter 2? Right? You guys remember chapter 2? And we talked a whole chapter about resonance. Okay, we talked about delocalization. Okay, so if I was to ask you to draw the two resonance forms of this ketone, you would say I have a pi bond between atoms of differing electronegativity. So you'd put in your square brackets like this, and you'd say, okay, here's my curved arrow, and then you would draw something that looks like this, and you'd say, here's my resonance form. Right? So remember, organic chemistry is an additive subject, right? You need to know chapter 2 to master chapter 14, so on and so forth. But if we take a look at these two resonance forms for this ketone, you see how in this structure it's got a double bond, but over here it's a single bond. So what's the conclusion that we draw is that the actual bond is somewhere in between a double bond and a single bond. And we remember that double bonds are stronger than single bonds. Well, if you're wondering what's the relevance of all of this, well, if we take a look at this ketone here, this is called a conjugated ketone. How many resonance structures could you draw for it? Huh? How many resonance forms could you draw for it? Well, the answer is because of the conjugation, you can draw more resonance forms, can't you? That's right, you can draw more resonance forms. So what's the conclusion that you draw? Is that with the conjugated ketone, you get one additional resonance structure. And so what that means is that this double bond here has more single bond character. So what does that mean? It means that that double bond, this one here, is weaker than the one in the ketone that is not conjugated. So what's the pertinence? What's the relevance? The relevance is this. If the conjugated ketone carbonyl has more single bond character, that means it's weaker. Okay, if it's weaker, it's got a lower F. If it's got a lower F, it's going to absorb at a lower wave number, and this one is going to absorb at a higher wave number. So when we have conjugation, what is something that we look for? When we have conjugation or additional resonance structures, that means that we'll look for an absorption at a lower wave number. Give me a thumbs up if you're with me on that. We're still uncovering wave number, my friends. That's what we're still talking about. Okay, all right. We're just jamming, just talking about wave numbers, okay, on a Monday morning. All right. So you see the same thing with any kind of conjugated carbonyl. If you don't remember what the word conjugated means, let me remind you. So conjugated means that we have alternate, double, double, single, etc. So double, single, double, single, double, single, right? So it doesn't matter whether it's with a ketone or if it's with an ester. You notice that the carbonyl for an ester absorbs around 1740 centimeters to the -1. We'll check it out. When it's conjugated, it absorbs at a lower wave number. Why would that be? It's because you have what? An additional resonance form that you couldn't draw with the ester itself. All right, so make sure you remember that. This is something that comes up all the time in organic chemistry, but not enough that it comes up. It doesn't come up every day, but it is going to be relevant as we move forward in the class. All right. So this is the table that's given, or this is the first part of the table that's given to you in the textbook, okay? It's table 14.2. Now, I'm not going to give you this table on your quiz. Remember, I'm going to give you the handout that is published in the chapter 14 module I showed you this morning. We're going to take a look at it again later. But these are, or this is the table 14.2. This is in your textbook. It's got kind of two parts that I spread over two slides here. And so let's just take a quick look at these. So we see that any bond to hydrogen, okay, whether it's an oxygen-hydrogen bond, okay, like as is shown here, you can see that that usually gives you a broad stretch, and there's a reason for that. It involves hydrogen bonding. I'll get to that later, between 3,200 and 3,600. If it's an oxygen-hydrogen stretch that's part of a carboxylic acid, get a finer tip pen here. If it's part of a carboxylic acid, so here I'll write alcohol. If it's part of a carboxylic acid, that's going to have an even broader stretch between 2,200 and 3,600. In fact, this is the easiest stretch to recognize in all of infrared spectroscopy. For an amine, whether it's primary or secondary, the stretches are going to be around 3,350 to 3,500. If you have an alkyne, so remember, this is an sp hybridized carbon. Like we said, it was around 3,300. If it's sp2 hybridized carbon hydrogen stretching, it's 3,000 to 3,100. If it's sp3 hybridized carbon hydrogen bonding, it's below 3,000, so just below 3,000. And if you have an aldehyde, you have this. We call these two. We have a special name for it. We call this aldehydic stretching. Kind of a funny word. Stretching. There we go. So aldehydic stretching. Those are two weak signals that are at 2750 and 2850. But if you have them, it's usually a giveaway that you have an aldehyde. Then we get into double bonds. Okay, what are the types of double bonds that are going to be relevant? Carbon-oxygen double bonds. Okay, well, remember we call this a carbonyl. So carbonyl. And carbonyls are found in what? They're found in carboxylic acids, esters, amides, ketones, aldehydes. So we have a whole range of stretchings, and I'll get into those in more detail in just a second. The next one is an alkene. An alkene, the carbon-carbon double bond stretch is between 1,600 and 1,700. If aromatic, so it says here aromatic. Now here it has a whole range. These ones here this is usually 1667 to 2000. These are called overtones, and they're very weak. Just put here weak. When we look for aromatic carbon-carbon double bond stretching, it's usually between 1450 and 1600, and it's usually 2 or 3 stretches. 2 or 3 stretches, okay? Triple bond is between 21 and 2200, and then this one here, if you don't remember the name of this one, this is called a nitrile. It's not a cyanide, right? Cyanide is a polyatomic ion. That's something different. But if you have a nitrile, that's it's usually around 2250, but 2200 to 2300. And then, like I said, for the carbonyls, Carbonyls are found in so many different compounds. You see anhydrides, acid chlorides, esters, aldehydes, ketones, carboxylic acids, and amides. I'm not going to go all through all of those. You can see they're all around the 1700 neighborhood. Then we have fingerprint region. So I told you the fingerprint region does have some relevance to us in Chemistry 3101. Most notable would be carbon-oxygen single bonds. If it's in an ester, so this is an ester or a carboxylic acid, but I'll just put here, if it's an ester, it's usually very strong, this stretch. It's oftentimes the strongest stretch in the entire spectrum. If it's in an ether or alcohol, it's usually 1,000 to 1,100. This one here is, of course, for an amine. Then we have halogens. Those don't come up a whole lot, but bonds to halogens, if it's chlorine, it's usually 600 to 800. And bromine is so stinking heavy, you know, it's got a mass of almost 80 atomic mass units. So that's all the way down to 500, okay? So again, are you going to have this memorized in a day? Well, Rome wasn't built in a day, so I doubt it. But, you know, should you have an idea of this by the time you get to the quiz? Well, yeah, but by the time you do all the practice, you'll have most of it in your brain anyway. All right, so that deals with wave number. I got two more things I want to cover before we take our first break. The next thing is intensity. I can make intensity and shape a lot faster, okay? The first thing is if your signal is strong, okay? Strong signal usually means that you have a strong dipole. Strong dipole in the bond, okay? Whereas if you have a weak signal, what do you think that means? It means you've got a weak dipole in your bond. And that's kind of the conclusion. That's really all you need to know, okay? It goes into more detail here in the slides, but all you have to know is that when you have a strong dipole, it creates its own electrical field, and it kind of acts like an antenna for picking up infrared electromagnetic radiation from the spectrometer. And so when you have a strong dipole, like in a carbonyl, right, you guys know there's a really strong dipole here, okay? We have a big dipole moment. So remember, this is dipole moment. So it oscillates a lot. And so you get a stronger signal. And if you have a weak dipole, right, this is isobutylene, that's got a very weak dipole, so you get a weak signal. So again, what you need to know about intensity can be summarized by this. The more polar the bond is, the stronger the signal. That's about it. Okay, that's really all you need to know for my class. Okay. You take a look at this alkene here, which stretches around, what did we say? Maybe this one's around 1650, something like that. And then you see this carbonyl here, maybe that's around 1720. Okay, we see both of those stretches, but you can see that this one is more intense since stronger dipole. That's it, man. That's all you need to know for this class, okay? Weak dipole, weak stretch, okay? There you go. And however, one of the exceptions is this: is if your bond is completely symmetrical, then there's no dipole at all. So if you have this molecule here, this molecule would be called 2,3-dimethyl-2-butene. Okay, but either way, you see there's no dipole whatsoever, right? Everything here is completely symmetrical. So just because you don't see a stretching frequency doesn't mean that it's not, that there's the functional group isn't there. Again, this is tested very rarely, but it is something you need to be aware of as a chemistry student. Okay, last one is the shape. Before we take a break, we'll talk about shape, because I'm sure you picked up on this, that some of the signals are just so broad. They have this kind of big rounded shape like this, and other ones look like you could, you know, hurt your finger on the end of it or something. They're so sharp. Well, why would that be? Well, really the only type of stretching signals that are broadened that we are interested in this class would be oxygen hydrogen stretching is usually really broad, and I'm going to add one to it, which is nitrogen hydrogen stretching. And what do those two types of bonds have in common? You guessed it, hydrogen bonding, right? Both of these can participate in hydrogen bonding like that. All right, so what's the consequence? Here is an oxygen hydrogen bond that's participating in hydrogen bonding, right? You guys know this is your hydrogen bond. And so what hydrogen bonding does is it weakens the bond. Well, what do you guys know? We know that wave number is proportional to bond strength. So if the bond is weakened, right, if it keeps going back and forth, if this bond participates in hydrogen bonding, then the hydrogen bond lets go, then it reattaches, so on and so forth, then what happens is that sometimes the bond will be weakened and sometimes it won't. Because we don't look at fluorine in the IR spectrum. We don't look at any bonds to fluorine in there. Yeah. So the hydrogen bonds are transient, right? They're just kind of back and forth. And so some molecules are going to have bonds that are really weakened and other ones don't. But we're talking about moles of molecules. And so what we see is we see a range of stretches, right? So that's why we get a range of stretching. Now, it says here, the OH stretch will be narrow if the solution is really dilute and there's no hydrogen bonding. This is something that comes up very rarely, but it's shown right here, okay? This, I don't even know the last time I showed my students a spectrum, but this means where it says free OH, it means not participating in hydrogen bonding. Most of the hydrogen bonding that we see is going to be really broad like this, and students can usually pick it up immediately, okay? And it's a bond between oxygen and hydrogen, like that. There we go. So if you take a look at a carboxylic acid, look at how broad the oxygen hydrogen stretch is. Look, it goes all the way from 3,600 all the way down to like 2,200. Well, there's a reason for that, which is shown right here, okay? So this is the hydrogen bonding between two carboxylic acids, between two carboxyl groups. You can see you have a hydrogen bond here and a hydrogen bond here. And so hydrogen bonding, it says here, hydrogen bonding is very pronounced where in a carboxylic acid. And so that's why the stretching is so broad. Okay, if we go back, okay, if you look at an alcohol, yes, it's broadened to a degree. Okay, if you see the alcohol, yes, it is broadened. There's no arguing that. However, if you look at the carboxylic acid, it's much, much, much more pronounced. Okay, you see it's extremely broadened. And I would wager that for my students who I've taught over the years, thousands of students, that recognizing a carboxyl group, so what you would say is, OH stretch, and then I would write carboxylic acid like this, just like they have written right here, okay, on the slide. Come on, acid. I'd say it's probably the most recognizable of all the stretches in all of infrared spectroscopy, okay? So if you think that's what you see, it's probably what you see, all right? So there you go. There's one more I think that we have to cover, yes, which is the nitrogen hydrogen bond. If you remember, we have two types of amines that I told you that are relevant in the infrared spectrum. One is the primary amine, and the other one is the secondary amine. Now, primary amines exhibit two nitrogen hydrogen stretches, okay? So for a primary amine, you usually see something like this and then like this, okay? So there'll be two stretches. And the reason why is that one is for symmetric stretching and the other one is for asymmetric stretching. Sometimes students will think, well, when I have a primary amine, there's two bonds between nitrogen and hydrogen, so two stretches for two bonds. That's not the reason why, okay? It's because of symmetric and asymmetric stretching. Whereas for a secondary amine, okay, a secondary amine looks like this, where we have only one nitrogen hydrogen bond. And so because of that, we only see one signal because there's only one nitrogen hydrogen bond. So that covers all of the background of infrared spectroscopy. Here's an example. This is a primary amine right here, and you see the two stretches. And then this one here is a secondary amine, and you see there's only one stretch, but what do they have in common? Is broadening, right? There's a little bit of broadening here and broadening here. Notice that the bonds are, the intensity is not nearly as great as with oxygen, hydrogen. Why? Well, if you go back to oxygen, has an electronegativity of 3.5, okay? Whereas nitrogen has an electronegativity of 3.0. So it's not as electronegative, so the dipole isn't as strong, and so it's not as intense. So what do we do when we're presented with an infrared spectrum? Here's what we do. If we're trying to find functional groups, the first thing we would do is look at the diagnostic region. Look above 1,500 reciprocal centimeters. Then we look for double bonds in this region, 1,600 to 1,850. Between 21 and 23, we look for triple bonds. So whether it's a carbon-carbon triple bond or a carbon-nitrogen triple bond, we look for bonds to hydrogen. On the far left, we might look for alcohol or carboxylic acid. Then we look at the wave number, we look at the intensity, and we look at the shape. Is it broadened? Is it sharp? Is it at 3100? Hey, that's an sp2 hybridized carbon hydrogen stretch. Is it at 3300? Hey, the carbon must be sp hybridized, so on and so forth. And so something that's really handy to do when you're analyzing an infrared spectrum is to draw a line at 3000, because then you can look above it and you can look for sp2 hybridized carbon hydrogen stretching, sp hybridized carbon hydrogen stretching. You can look for primary amines and secondary amines. You can look for bonds between oxygen and hydrogen, whether it's an alcohol or a carboxylic acid. And of course, you can look for the ubiquitous sp3 hybridized carbon hydrogen stretching that is usually shown below, or is shown below 3000 reciprocal centimeters. So something else you can use IR for is to distinguish between two compounds. And if I was to ask you guys to identify the functional groups, here you would say this one has an alcohol and this one has a ketone. Well, you could actually monitor this reaction using a TLC, right? But let's say you wanted to use something a little more modern, you could use infrared spectroscopy, because you know that this stretch is going to be broad, right? This is going to be from 3200 to 3600 reciprocal centimeters, whereas we know the carbonyl stretch is going to be around, let's say, 1720 reciprocal centimeters. So what you would see over time in your infrared spectrum is that this signal would disappear and this one would start to appear. And once this one is completely gone, you would know the reaction is completely done. If you're wondering, have I ever done this? The answer is not really. Okay, no, I would usually use NMR to do this, or a TLC, but it can be done. And there's actually something nowadays called an infrared probe, where you have your reaction mixture stirring. So let's say you have your reaction flask like this, and then you have your reaction. And here you can actually stick an infrared, it's called an infrared probe. You stick it in there, and then you can actually watch the IR in real time. So you can actually watch the signals disappear and the new signals appear. But again, it's something I've never used. I don't know what a probal is, but a probe like that. Anyhow, so something kind of interesting there. So what we're going to do now is take a short break. Come on. Go. Okay, so I'm still sharing my screen, but I'm